Thanks. I hope at the end of this, you won't ask yourself, what am I doing here? And if I have too many slides, it's because guests have dipped into my speaking time. I believe. But thanks for having me. It's a very nice seminar series, which I've attended also a couple of times. And especially the IT setup, the tech setup was very. Well, yeah, so I've been in Vienna now for whatever, 8 months. Still feels like yesterday. Lots of learning, certainly lots of lecture preparing for teaching. But I guess within this setting, I can immediately start by telling you what motivates me, what kind of science is interesting. So I am a surface scientist by training and creed. I'm interested by putting things on surfaces, right? As the saying goes. But obviously, it's more interesting if the things you put on surfaces do stuff. And of course, in catalysis, we're very much interested in overcoming barriers. To reduce the barrier, you've reduced a lot of barriers, and it's not very selective, right? So there's a variety of different ways how to make catalysis more selective. And photocatalysis is one way, sort of beating Boltzmann, despite being at the University of Vienna. It's good to fight against Boltzmann every once in a while, selectively trying to deposit energy in a non-equilibrium way. And the same goes for electrochemistry. The thing is, you shouldn't say this in surface science, but sometimes it's good to look at gas phase chemistry. It's very inspiring because they're always 20 years ahead, right? So if we try to do vibrationally selective chemistry and surrogates, they did it ages ago, so that they managed to produce specific reaction outcomes by activating certain vibrations. We might also be interested to actually drive chemical reactions through coherent quantum control, also something that has been a field of studying in gas-phase chemistry for ages, but far away, like miles far away in condensed phase and surface chemistry. And so we should hope that there's also modern experiments that help us to get closer to that and that motivate new theory. And there's many of them, I always sit in between chemistry and physics in what I do. There's a lot of exciting experiments in chemistry, but unfortunately, not very well designed catalyst conditions. Everything's a bit messy. So we often look to idealized model catalysts to study processes in more detail, where we can selectively pump electronic excitations and probe how molecules respond to excitation and how that leads to a cascade of energy transfer processes from electrons, from light to electrons, from electrons to vibrations, and how these vibrations pass on the information and the energy. And it's a very exciting time to be a theoretician because there's so much more interesting spatially and temporally resolved experiment. Both lab-based and also synchrotron, large national facility-based studies. So our job is to develop simulation methods that are able to predict measurable observables, right? Emphasis on the measurable. Otherwise, it's not theory if you can't measure it, if you can't compare it to experiments. So what are good measurable observables? Well, that's a good question. That is sometimes not so easy to answer, because now the problem with these experiments is also that the signal becomes very convoluted and messy, right? So often you don't even know what the corresponding observable is. A good playground for us is hydrogen metal chemistry, not just because there's decades of old experiments from IBM and from Bell Labs and from many different places, and it's easy to prepare, but also because it's simple and helps us to kind of find interesting quantum effects. If we look at reactive dissociative scattering on surfaces, we can see if we get the barriers right. We can see if there's non-adiabatic steering effects where electronic excitations tell you where the direction of travel is for the molecule. There are quantum nuclear effects, isotope effects to study. There's also really interesting studies on laser-driven hydrogen evolution if we're interested to understand if light-driven chemistry can produce selectivity in reactions. There's a lot of old and still good experiments. Unfortunately, not very many new experiments, but something to work with here in that space. And so the chemical design space for us, if we want to understand how to control ultrafast dynamics, the process starts from light, right? So light excites electrons in the catalyst, and this excitation triggers a cascade of a lot of different processes that involve. You have a plasmonic resonance, or if it's a metal, you have non-equilibrium distributions of electrons you can create. These electrons can be directly created in the catalyst. They can also be created such that they introduce charge transfer across the interface. But these are normally quite short-lived, such that they equilibrate through electron-electron scattering to something we call a hot electron distribution. So thermalized electrons, but out of sync with the temperature of the lattice. And because the heat capacity of electrons is bad, this could be thousands and thousands of Kelvin that are produced at very short time scales in the electrons, right? And of course, it depends on the morphology of the nanoparticle and so on and so forth. And then over the scale of picoseconds, these very hot electrons equilibrate with the lattice through electron-phonon coupling to bring you back to equilibrium. And so far, I haven't talked about chemistry, right? So at every single point in this picture, you could imagine communicating with molecules. You could imagine that there are coherent quantum dynamics, strong field enhancement, strong field effects that affect the molecules at the surface. You could imagine that non-equilibrium electron distributions directly lead to charge transfer into molecular states that then sort of make or break bonds. There's also scattering phenomena where these thermalized electrons populate molecules, but there's also rather boring photothermal surface heating, right? It's just heating your lattice and therefore by Boltzmann factor increase reactivity. And so the answer, which mechanism is the most important one, is of course different for different catalysts, different molecules, and different combinations thereof. So that the science space in terms of materials discovery is one where we might want to try to engineer systems that have particularly long-lived non-equilibrium electrons, if we want to understand what this mechanism does, or we want to be able to tune the light metal coupling and the electron-phonon coupling such that they are balanced, that the electron-phonon coupling isn't too strong, basically siphoning off all of this energy into the phonons, heating your lattice and not producing any interesting non-thermal chemistry. And we want to be able to control where the energy goes, where does the energy, where does the charge, where does the spin go. So it's an interesting playground to explore different elements here, and this could thermalize electrons. What if I only allow ultra-subtle processes? And in terms of methodology, my background is in electronic structure method development. We have for many, many years tried to understand, develop methods to study hybrid organic, inorganic interfaces, molecules at various different surfaces, and particularly excited states response properties of molecules at sad surfaces. And to be honest, for many years, we're still even struggling to just predict the structure and the stability of these molecules, the ground state, not even response properties, right? That's hard enough. And we try to couple this with so-called non-adiabatic or mixed quantum classical molecular dynamics methods, where we try to study how these excited electrons exert forces on the atom. So how do hot electron effects change the forces that are experienced by adsorbates? And of course, we need to understand how light excites hot electrons or holes, which of them at which energy, how many of them, and how does it depend on the morphology of the crystal. And all of these things, could keep you busy for a career's worth of work. And we have used some of these methods in the past to study things like single molecule, nanochemistry, surface nanofabrication, molecular photoswitches, nanoelectrochemistry, but even things as nonlinear spectroscopy and where does the energy go if I excite an infrared vibrational motion, where does the energy dissipate at the surface? And most recently, we're quite interested in this idea of hot electron catalysis or hot electron chemistry, where the coupling between vibrations and surfaces is very, very strong. And if I am able to excite electrons in the metal, I could potentially selectively activate vibrations on the surface. And one of the tools we use to kind of make this possible is what I call machine learning of electronic structure. So creating surrogate models of electronic structure that go beyond energies and forces. So all of the different ingredients we need in these different types of theories that we would otherwise throw away if we just were to look at an interatomic potential. So the idea is here laid out. You know what they say, if you have visions, you should go to the doctor. This is singular vision, so that's okay. So basically, we try to create electronic structure emulators of electronic structure that allows to very efficiently look at quantum operators that we might need as ingredients for our dynamics, think of excited state energy landscapes, nonadiabatic couplings, electron-phonon coupling tensors, etc., etc. We couple them with mixed quantum classical dynamics methods we developed and simulation methods of light matter interaction. And the idea is that, in one sweep, we're able to simulate how light excites electrons and how these electrons drive dynamics. And this is quite a challenge because these are processes that evolve huge orders of magnitude of time scales, right? We're going from the attosecond to the femtosecond, all the way up to picosecond dynamics or larger. And ideally in a way so that we can switch off certain mechanisms in the process. So the starting point is, of course, dynamics. Classical dynamics, we're propagating equation of motion. And normally the way how we would do this would be ad initio molecular dynamics. So at each and every point in time across the dynamics of the nuclei, we evaluate a potential as an expectation value of the Hamiltonian, and we evaluate the potential of the ground state. And this gives rise to the beautiful concept of the potential energy landscape that is kind of the foundational principle of chemistry. Everything in chemistry happens on a landscape. And machine learning potentials have revolutionized how we access these potentials by basically allowing us to take electronic structure theory data and mapping it onto scalar fields and vector fields that smoothly represent how particles evolve. But in the process, we throw away quite a lot of stuff that we've taken a lot of time and effort to evaluate. So it's a shame to not use this as well. And I'm going to get back to this later. So we can think of machine learning here as kind of an accelerant to allowing us to study the things we would do anyway, but now we do them faster. Here's an example. If we want to study reactive chemistry on surfaces, some of it, it involves calculating reaction rates. Reaction rates can be very low, and they're non-equilibrium processes. That means if we want to study the sticking probability of a molecule, we might end up having to calculate a lot of trajectories to get to this point, especially if we're looking at things like quantum state resolved processes with specific vibration rotation states in the scattering. And I don't need to go through the maths with you, but doing it ab initio MD is hard. Imagine you have 10,000 trajectories, you have multiple translation energies, specific quantum states. Everything is impossible. Even a single trajectory is unfeasible at the time scale of a PhD student project. So we and many others use machine learning potentials to enable some of these things. And it's not just about doing new things, it's about doing the things we would normally do properly, statistically significant sampling, right? Uncertainties, etc., etc. The things that you care about when you look into the mirror in the morning or in the evening. And of course, active sampling, active learning is one possible way to do that. We build potentials for various facets of copper here, for example, to study reactive hydrogen chemistry of copper. We study all and create new data and insert it into our potentials. And most importantly, we propagate uncertainties, both aleatoric and epistemic uncertainties. So that means approximation error and statistic errors all the way into our dynamic observables, such that we have an understanding of, what's there about how much can we trust the data. And that's something that I think is really, really important to mention also to experimental colleagues. The result of this looks different for different observables, right? So the kind of data you need to describe one type of measurement is not the same as the kind of data you need to describe another one. And so when you talk with people about convergence, or you should always say convergence with respect to a certain quantity, because it's always a different answer. And so machine learning potentials allow you to bring this bar down. Depending on which potential you use or which architecture, there's some variation that is quite significant. And so I don't need to tell you much about machine learning potentials at this point. Everybody knows about them. But in principle, we are able to describe sticking probabilities, activation energy barriers very accurately if we do it right. Every single point here would be tens of thousands of trajectories that we simulate, which would be unimaginable, and everyone comes with a nice error bar. These equivariant models that exist, graph neural networks, they're smooth and they're accurate and quite generalizable, transferable across materials as well. So we're in a good place. Yet still, the number of data points we require for them are very large, thousands and thousands of data points. So we ask ourselves, can we increase data efficiency? And this is where these foundational models come in. I put this always in quote because computer scientists would kind of protest to the term foundational model for this. They're just models trained, they're very, very large, and they're trained on very, very diverse data, right? They're not semi-supervised. Every single data point is labeled. And the ambition here is to create the kind of universal force field for things that can break bonds. And we can see if we use them, the barriers are off. So we don't get exactly the answer we need, but they're also not exploding. So they're stable, right? Which is more than you could have asked for decades ago, or actually a few years ago. And so we ask ourselves, can we use these foundation models to create accurate and transferable machine learning potentials with very little data? And so one approach here is that we take the existing foundation model, we freeze out certain parameter groups that we know the model has trained and that contain information on the atomic environment, the representation that's universal. And we then just train certain parameter groups that we think are relevant for the bespoke problem that we have in mind. So let's imagine we have a machine learning model, a foundation model trained on all materials project data across diverse sets of materials. And we now say, can we train this in a bespoke way for our H2 on copper reactive chemistry? And so the original data set we had before when we did active learning was about 4,000 data points. And this would be the 100% data. That's 4,000 data points. And this is our original bespoke model that we trained from scratch that reaches this error. So here's different flavors of freezing out parameter groups in the model and what kind of errors we achieve with what kind of percentage of data. And we see that with the foundation models, we already start at a low force error, which is remarkable, even with high amounts of data. And we, at 10% data, we can basically achieve the same accuracy as we would otherwise achieve with 100% of the data. So we can get away with hundreds of data points, or obviously it's a very narrow scope of the model, which for our case is fine, right? You always need to ask yourself, what is the scope of the model and what is the target question? And so a lot of the things we teach our students haven't changed, right? Yeah, maybe you don't have to worry about certain things anymore, but the question of what the hell is it that I'm trying to model is still an important task to learn how to answer that and how to approach this problem. So we can pretty much get the same type of analytical observables and accuracy with 10% of the data now. The problem is that these foundation models are huge. They're terrifically slow. So if you're trying to run millions of trajectories, this is a pain. So we have a workflow where we now build these foundational models by fine-tuning with little data, and then we distill the model onto a more efficient circuit model. Distilling means we now basically treat the fine-tuned model as our new ground truth. It's the oracle that gives us all the energies and forces. And we transfer everything onto a much more compact and efficient model that we can run task per out onto lots of simple computers to solve our problem. And of course, now you can see the cascade of models is large, so it's very easy to mess up. So it's important to validate and have good error control across this whole pipeline. So much for the adiabatic dynamics. But if you're interested in photochemistry, that's not the answer. I already told you we need excited states. And we need the effect of these excited electrons. So one way how to treat this is to basically do the so-called mean field approximation. So instead of calculating the potential that our nuclei feel with respect to the ground state, we just calculate the full expectation value of all of the electrochemical states. So let's assume during our dynamics, let's say a molecule comes in, scatters from the surface, excites electrons, or light comes in, excites electrons. The many electronic states are involved in the wave function, and the effective potential is a mean field average of all of these different excited states involved. You can do that. That's the zeroth order approximation. The problem is it's almost never right when there's interesting chemistry. It by definition cannot be right because interesting chemistry always has multiple outcomes. So you can either react or cannot react, you switch or not, you don't switch, bonds break or they don't break. In Ehrenfest dynamics, in mean field dynamics, it's always a halfway house. Basically, everything happens a little bit. So if I have a particle that scatters from a surface that has a chance of picking up a charge, then the outcome is it either picks up a charge or it doesn't pick up a charge. In Ehrenfest, it picks up half a charge, right? So that's not really helpful because it's unphysical. So the other approach we have is to go beyond the mean field approximation by correctly sampling the quantum distribution of electronic states involved in an ensemble way. So that means over the course of the dynamics, I sample all possible electronic states by the weight by which they are involved. But each individual trajectory, each individual molecular motion only ever sees one energy landscape. But that energy landscape can change to accommodate this changing distribution of electronic states. So if I'm here, I might only see ground state energy landscape because everything's in the ground state. If I'm here, there might be a certain percentage of trajectories, a certain contribution from an excited state. So a certain percentage of trajectories should reflect this on average statistically. And so notice the tiny little difference between the top and the bottom is this parenthesis key. That means now the way how I calculate the potential of a specific state is sort of a function of time. But I can hop between these different states. There's a third option. I can also go and say, well, I have lots of big particles, atoms, and I have lots of very small particles, electrons. And when you normally have very big particles, very small particles, you can ask yourself, and the small particles are very fast as well, you can ask, do I actually care about the explicit dynamics of the small particles? Can I not just coarse grain out the small particles? And when you do that, normally you end up with a Fokker-Planck equation, which you can always kind of map under certain conditions, map onto a so-called Longitudinal equation, where we now look at the classical equation of motion that has additional components that relate to the fact that we treat the electrons now as a thermalized bath. So our electronic excitations, we have a bath of electronic excitations that give it or take it energy from the dynamics. And the dynamics, of course, evolve under some sort of potential energy landscape that isn't allowed to change. So this is Ehrenfest, but even weaker. So this is Ehrenfest, where we make a weak coupling assumption, where we say that the potential energy landscape is not allowed to change, not even a bit. It's still the ground state energy landscape, but there are additional forces where the electrons bump into the nuclei and they help the nuclei to make it up a barrier, for example, right? And so our task now is to calculate this quantity here. This would be normal force. This is the velocity times some sort of quantity. And this quantity is called the electronic friction tensor. So it tells you the strength of coupling between these electronic excitations and the nuclei. And it's a function of all possible positions of the nuclei. It's related to electron-phonon coupling, right? Because it tells you how the electrons couple to the phonons. And you can calculate it from DFT. It's an absolute nightmare to calculate from DFT because it's what we call a Fermi surface integral. Normally, everything's a nightmare in electronic structure theory because you need to integrate over the whole, infinity of electronic states. But this is even worse because you need to integrate over the infinity of states that sit in the infinitesimal shell of the Fermi surface. So it's on top of being expensive, it's also very hard to write. So this kind of equation doesn't do justice to the complexity of this problem. But basically, it means calculating complicated matrix elements at large scale for systems and then making this sound magically converge. We have over many years implemented code that does it at large scale and code that now is able to do it for hundreds and hundreds of atoms. This is also an important ingredient if you're interested in things like superconductivity, Alan Dines or Eli Ashbeck theory. So we are now able to calculate critical superconducting critical temperatures for massive incommensurate random alloy systems that we're now sort of exploiting as well. It's a nice side thing that came out of this. But in principle, what we need to do dynamics is we need to calculate a machine learning surrogate of this thing. It's in the nature of friction that it's related to a diffusion process. And so the way how we set it up is that this friction tensor, this relaxation rate tensor, is a self-adjoint product of what's called a so-called diffusion matrix. This matrix describes kind of the diffusion process that the electrons describe. And it has some nice symmetry properties. It's real valued symmetric, positive semi-definite. That means its eigenvalues have to be either 0 or positive, because each eigenvalue describes a sort of relaxation rate, like how much does the energy of a phonon decay if it's interacting with nuclei. And so the way how we represent these diffusion matrices is through a linear least squares fit. We fit these coefficient vectors times some sort of atomic environment representation matrices that satisfy all of these symmetries. And they're not just atomic environments that tell you how the constellation of atoms around an atom changes this friction. They're also bond environments. So we need to calculate these elliptical environments around bonds because the friction tensor, of course, has on-diagonal effects, atom with itself, but also between atoms. So it's not Cartesian diagonal. But this approach is linear transferable size against. I like the fact that the quantity that we feed into this process is incredibly noisy because it's very hard to converge with BFD. So what I'm showing you here is AO's lettering on gold. NO comes in, vibrations are excited, comes down. This would be this D component. There's the center of mass component. And basically, I'm putting the machine learning model prediction on top of this ab initio trajectory. And it's a very nice fit. I hope you agree with me. We can do the same with H2 scattering on various different facets of copper. It's a single model that describes all these different facets and higher index facets as well. And we correctly describe this modulation. There are still some errors, so we're still tricky, but these errors are basically within the noise of all of the other problems we have in the dynamics. Because if we want to get this down, we first need to go back to the DFT to fix it. So what can I do with this? I can go back to some good old-fashioned data, and I can try to see how close I get to experiment. So for example, I can look at survival probabilities of the first excited, vibrationally excited state of H2 by scattering from 110 copper. And the star is an absolute measurement. It's not scaled or shifted or calibrated. The pluses are scaled or shifted or calibrated. It's easy to get them right? As long as one of the collision energies is right, you just move the whole thing. The absolute one is the heartbeat, right? This is the one with this arrow part. We can do the same for copper 100, where we also have nice agreement with all the absolute energies compared to previous non-machine learning potentials or machine learning potentials that were trained in different ways. This would be the transition probability, rotationally inelastic transition, where I have a molecular beam of J equals 1 to J equals 3 that we can get right across that, even to higher collision energies. So this is all public. It integrates with lots of different dynamics packages you might be using. And it's now pretty straightforward from tutorials how to build these types of models. The question I started with was sort of non-adiabatic effects, excited state effects. How do electrons change the dynamics? Is there any steering? It turns out for H2 and copper, it's very little. So even if I look at the most sensitive thing, which is vibrationally inelastic de-acceleration of V equals 2 to V equals 1, the collision energy dependence changes very little from an adiabatic to a non-adiabatic reaction. So this would be experimentally impossible to resolve, right? So it's not a nice playground. The story is H2 hemisolves too strongly, such that there aren't strong steering effects in the dynamics. But we can turn this process around. We can look at light-driven hydrogen evolution with this process. So we take adsorbed hydrogen at various different coverages. We couple it to kind of an electronic bath and phonon bath. We drive the electronic bath with a laser that exactly creates this electronic temperature. And with all of the machinery ingredients we have, Alex can now calculate the desorption probability as a function of fluence, as a function of surface facet, as a function of coverage, etc., initial temperature. And every single point here, again, is tens of thousands of trajectories. So it's a really interesting tool that allows us to dig into some of the mechanisms here, where we basically see how when the laser hits, we get the peak temperature at the end of the laser. At that point, we've transferred substantial amounts of kinetic energy into the adsorbates, and the desorption process happened in a delayed way straight after that. If we look at the actual diffusion dynamics that occur in response to the laser, this is kind of what I'm showing in this single trajectory here. So we're looking at H2 so the laser is at 0, right? So we're now looking at the diffusion dynamics. You can see how the kinetic energy heats up, the molecule starts to heat up, it gets mobilized, it starts to diffuse, the atoms start to diffuse around the surface. So that's what happens here. And eventually we get into this reactive region where the two H atoms collide, we meet each other. Now, what's interesting is at the point where they meet each other, electronic friction and nonadiabatic effects don't matter. And that's because at the point where they get to the transition state, if we zoom in, there's almost no contribution to the work due to this electronic friction force. That's because at the point of the reaction barrier, the velocities are very, very low. And if you remember, it was friction times velocity, so it contributes very little to the steering effect here. But of course, the friction gets you to that point. You wouldn't get to the barrier without it. And we're currently trying to analyze how much is this effect a consequence of coverage and different effects. So we recently looked at vibration lifetimes in electronic friction as a function of coverage on tungsten and molybdenum surfaces. And so basically what I'm plotting is the electron-phonon lifetime of different molecular vibrations, which you can calculate very accurately. And we're hoping that some people might be interested to measure that for various different surface modes of this collective overlayer. And some of these modes actually have a vibration lifetime that's very sensitive to coverage. So basically at full coverage, there's basically no electron-phonon coupling, which is really interesting, isn't it? And the reason for that, there's some interesting electronic structure reasons you can ask me about later if you want. But basically, we can see that as a function of coverage, the vibration line width changes dramatically. And so therefore, also the anisotropy between different modes changes. And some modes might be, if you look here, some modes might at high coverage still be very, very sensitive to picking up energy from excited electrons, while others are not. So you can see here we have a much more anisotropic mode where this vacuum mode on molybdenum is happy to accept all sorts of energy the electrons have to give, or happily releases it to the electrons, while others do not. There's many, many more problems with electronic friction. I could fill a whole talk about all the things that are problematic with it. And we're still working on going beyond the Markov approximation and finding other fixes. For example, it only works for perfect metals. It doesn't work for semiconductors. It doesn't work really well for molecules where you basically have where the energy landscape changes due to electron transfer. And it also doesn't work well for oxygen-terminated, oxygen-powered surfaces here and of the oxides. The problem is it's very hard to assess when it's right and when it's wrong, because the experiment we normally compare to is an energy loss distribution. So you have a molecular or atomic beam, you scatter from the surface, and you measure the amount of energy that beam has lost. And as a fun, you basically get some signal that says that many hydrogen atoms make it back without, elastically, without losing any energy, or with losing almost all the energy. And the problem is this signal is very integrated. At finite temperature, it's very easy to get this right. Actually, it turns out we did some playing around, making even artificial, unphysical friction, and we still sort of got it right. So what you need are low temperature experiments where you have a clean scattering experiment where you have a single bounce effect. And then you see hydrogen atom hits once, this is the amount of energy it loses. Hydrogen atom hits twice, this is the amount of energy it loses. It bounces twice, it bounces 3 times. So we have enough resolution to actually unpick the different mechanisms rather than having a big blob that everything gets right. Like every single peak here is single bounce, double bounce, triple bounce effects, different types of trajectories we need to unpick. So with some of the experiments, it's not even wrong because we don't know what it is. The other interesting thing we're trying to handle at the moment is spin. So what happens to the spin of the hydrogen atom or to any open shell molecule? Hydrogen does have a spin. You will agree with me, right? If it comes to the surface, that spin does different things depending on the surface. On the gold surface, you basically get screening of the spin. There's nothing, but the effective spin state has changed. None of the friction models at the moment account for that. Yet some of them are really right. So are they right for the wrong reason with the experiment? I don't know. We're currently also looking into magnetic surfaces to understand this. We have ways to go beyond friction. One of them is this surface hopping approach that I told you, and we need to cut quite a lot of corners to get to a form of surface hopping that you can use on condensed phases, in particular in metals. If you've ever seen talks by other distinguished colleagues in Vienna, when they talk about surface hopping, they will have a handful of surfaces, right? maybe 2, maybe 3. And you have very, very good quantum chemistry to describe these surfaces. We have infinitely many surfaces, and we have terrible electronic structure theory to describe them. So sort of that's the starting point. And so what we do is we map our electronic structure theory onto simple Hamiltonians, which are effective, non-interacting and electron Hamiltonians. The good old-fashioned Anderson-Holstein model or Hubbard models that where we then basically have our adsorbate impurity state and the metal state and coupling between them. There's no correlation. We treat them just as n electrons that behave together like an electron Fermi system. But we fit them such that they give us the correct energy landscapes and that they behave correctly according to the little data we have. So if I chemistry, I have an NO molecule that I can move up and down the surface, and I can also make it vibrate, right? So it's this thing here. So this is the bond length of the molecule, and this is the height from the surface. And this is classically the MD. The molecule comes onto the surface, it scatters elastically, and you can see that the amplitude of the vibration motion is unchanged. So this is no energy is transferred at the end. If I do the same with surface hoppings, basically at the point of the collision, the electronic state vector of the surface changes of excited electrons. And when the molecule returns, its vibrational amplitude has effectively been reduced, meaning that energy has flown from the vibration of a molecule to the electronic continuum of the metal. I've excited electrons. At the simplest possible model Hamiltonian, we can make a double well potential where this is the distance from the surface. We throw an atom onto the surface and it has a potential to get into this chemisorph facet. And depending on the coupling between the electrons and the motion, I can change this barrier, right? And basically the two energy landscapes U0 and U1, they describe the neutral case or the case where the adsorbate picks up a charge. When it picks up a charge, it becomes binding. If it stays neutral, it's always repulsive. It cannot adsorb. So it needs to pick up a charge to adsorb. And basically this parameter gamma here tells you something about the hybridization of the state. So if gamma is large, then it's very strongly hybridized and it kind of mixes very well with the metal state. If gamma is narrow, it basically spot on single state. And so if I diagonalize this with a continuum of metal states, I get the ground state energy landscape, the first excited, the second excited. Yes, I actually took out a couple of states. This is a continuum, right? But you basically see that as I go up, this curvature changes. So you could see how if I excite electrons, the dynamics will change. So let's take an experiment. Let's take a parting, let's throw it at the surface and see what friction do and what surface stopping does. So I throw it at the surface with a certain kinetic energy, and I measure how much kinetic energy it has lost, the percentage of kinetic energy loss. And you can see it came back on a higher state, so it's lost energy by exciting electrons. It turns out friction gets this fundamentally wrong when you go into the limit of very small gamma. So if we look at the pale green curve, you can see that the surface hopping and the friction disagree, and the friction starts to collapse onto this black dashed line. What is the black dashed line? So basically, if I use friction, at the small gamma level, I get something that's called the infinite stopping power limit. I get a singularity here. That basically means the particle stops mid-air, has no kinetic energy, and then it rolls down the hill again. And whatever energy it collects by rolling down the hill is whatever kinetic energy you get back. And that's this dashed line. That's the limit of losing all energy and coming back down the hill. And this is what you get at the low gamma limit with friction, which is incorrect because correctly, of course, if the coupling regime is very narrow and you have enough kinetic energy, you just pass through it and you don't see much of it and you come out on a higher diabatic surface. So basically, there are limits where if the gamma is too small for the kinetic energy and the vibrational energy in the system, then you're just not able to use this weak coupling approximation. And we can quantify this correctly. We can compare various different methods in their ability to describe friction, but of course we compare them against each other, which is not very satisfying. So what we need is accurate quantum dynamics, numerically exact. And so we compare with the group of Michael Toss, who can do hierarchical equation of motion, quantum dynamics, including nonadiabatic effects. And for the simple 2D pogo stick model I showed you, he can effectively give us the right numbers, right, which are these black dotted lines. And then we can start to compare our different flavors of mixed quantum stochastic approximate dynamics methods. How do they agree? Do they get it right for the right reason, etc., etc.? Now, to be honest, I shouldn't have plotted the histogram of experiment here, because this is a 2D model system. The experiment, much more high dimensional, and being close to experiment doesn't actually mean being right if you're comparing 2D versus ID. Here's another example. We're venturing to semiconductors, very exciting. So we basically use the same models to describe a germanium surface. So now we're looking at hydrogen atom scattering, kind of reconstruct the germanium surface, particularly at this rest atom site at germanium. We set up the model Hamiltonian such that it has a band gap, but such that enough kinetic energy allow you to overcome the band gap. So if you get into the closed chemisorb region, you're starting to basically allow the kinetic energy to excite the electrons. And we basically see that Ehrenfest completely fails to describe this, because at any possible energy, Ehrenfest will leak energy. But with surface hopping, only once you hit the band gap energy with the kinetic energy can you leak energy, because you need enough energy to overcome this gap. And we can compare the experiment with our little 1D model, and we see that we get this inelastic scattering effect compared to experiment right at low kinetic energies, maybe not exactly at high kinetic energies where other effects matter. So, from the experiment, this would be the elastic scattering peak, where there's no nonadiabatic effects. This would be the inelastic signal. So if you're below the band gap, you only get the elastic signal. You have no double peak. We can go to even higher dimensions. So we can build these simple lattice Hamiltonians for a high dimensional surface chemistry problem. Here we look at CU scattering on gold. We use constrained DFT to build these neutral and anionic diabatic surfaces, and we embed them into the manifold of metal states. We machine learn them with neural networks. And then we can, again, do our tens of thousands of trajectories where we look at CO initialized in a very, very high vibration excited state scattered from gold as a function of kinetic energy. And we look at the distribution of final vibrational states that are created in the process, where we can compare experiment against ab initio D and against surface hopping. And we can basically see that ab initio D gives you virtually no energy loss in the single vibrational quantum limit. But these are very, very approximate Hamiltonians. The simple lattice Hamiltonians, they don't capture the full band structure of the problem. So we're working hard on making better models. One is by making better parameterization of these models, making more reflective of also the state crossings within the metal states, and bringing correlation back in. But we also have methods to explicitly, build surrogate models of EFT electronic structure. And if you're interested, next week I've been seconded to talk about that a bit more. So we're really trying to go from atomistic machine learning, where we throw out interesting electronic structure information, to what I call electronic machine learning, where we take exactly this information and we try to build surrogate models of quantum operators. So this might be, for example, the Hamiltonian, or any other expectation and any other observable that can be articulated as a function of the Hamiltonian, the wave function, to describe things like band structure, densities of states, you name it. And in the interest of time, I'm going to now do a bit of cheeky jumping over some slides. And I conclude by saying that there's still a long way to go, right? In terms of simulations we want to do. And MEX is an exciting space where a lot of theoreticians with different interests and different expertise can come together and try to bring these methods together. We're interested in continuing to look at light-driven dynamics, but also dynamics driven by electrochemical potentials on surfaces, and in particular this question of inoperant stability of photocatalysts. So what happens to the morphology of your surface, to your nanoparticle, if it's exposed to these reaction conditions for a long time? Thanks.